especially, so let's step back. When I came to Western Allied in '94, we used the telephone, US mail, and the fax. The internet started to become prevalent right around Y2K, and today we use text, we use email. You occasionally might use the US Postal Service for something that had to be wet signed. And how else do we communicate? That's about it? I don't know. So we often underestimate the importance of the cover letter on email. Because usually, well, not usually, frequently, when you email somebody, there's an attachment. Like if you're sending them a proposal, or you're sending them an RFQ, or an RFP, or a RFI. I mean, there's all kinds of these initials, right? You really have to pay attention to the little cover letter that comes with it. It might only be 2 sentences. It might simply be something like, here's that letter, that submittal, whatever, that we talked about, right? That might be all it says. But if you are asking somebody to do something, then you have to give thought to what the couple of sentences are, because you are predetermining their attitude when they open your attachment. So, this thing, now, do we want to email like a CEO? Remember, the CEO, almost everybody that they're emailing is their subordinate. You don't really want to sound like you're their boss if you're not. But what the point that's valid in all of this is not being, well, first of all, clarity. You want to be clear. But second of all, you don't want to be, here's a good example. Let me find the one I was looking at. Shit, I can't even see it now. Take my glasses off. Okay, so you come down about to where the guy's crotch level is there, and it says, I was just wondering if maybe. That's not going to get you anywhere. There was one in here that started off with something to the effect of, I'm not an expert, but. Or, I don't even see it now. Oh, there we go. A couple lines below it says, I'm no expert, but. Well, bullshit. We are mechanical contractors. We are experts, right? I mean, that's just wishy-washy, crappy, terrible phrasing. The fourth one down is a common one we might be involved with. But instead of saying, sorry for the delay, we don't use the word delay. That word is not in our vocabulary. They suggest thank you for your patience, and that's not bad. But there are other things that you can do when you are talking to your customer. Now, on the other hand, the word delay is really appropriate if you're talking to your vendor and they posed you on a shipping date, right? There, it's totally okay to use the word delay. Like, do you understand what this delay is costing me? And you put that in the message line, right? And then you go on from there in the body. The one at the very bottom, where you say, please confirm you can meet this deadline. We don't communicate often enough with our vendors using the word deadline. How serious are they going to take you? How serious are they going to take when the commitment they made to get you the submittals by whatever, or to get the order placed, or to get back with you for where the schedule is? Or, how many things are you waiting on your vendors for? Many, right? If you don't use the word deadline, if you don't use specific dates, am I going to have this by Monday, right? It will just float. So your speak to your vendor is a lot different than your speak to your customer. But again, a lot of the ones down the left are really weak in terms of just even clarity, right? As well as making you look like you're an idiot. I was just wondering if maybe. So anyway, I like that. I'll leave you with that. I don't know where all of our group are, but we seem to have lost them.
I can go make their rounds.
I just sent an email, so.
Yes!
I don't know. I'm not expert on time, but I think 11:45 is what you're supposed to do.
So I'm going to start off with correcting old information that I gave you. Mr. Sanderson pointed out to me that I was about at least 2, maybe 3 Title 24 revisions behind in how heating CFM is established. And then I went from him to Mr. Sabisma and Mr. Arvid, and while they weren't different answers, they weren't all identical either. And so there's some understanding that goes with it. Here's how, what I told you last time is that with VAV reheat systems, we pick a heating CFM, a fixed heating CFM. That is wrong. What we pick is today, in accordance with, so ASHRAE came out with guideline 36, which is their energy efficient sequence of operation book. And there's, I don't know, 80 sequences of operation in there, some number like that, for all kinds of different things. But one of them has to do with VAV reheat control. And Title 24 adopted that. And so what it calls for is, instead of a fixed CFM, and you'll recall that we got a VAV box, we got a reheat coil, we got air, we got air. And remember, there was a max CFM, there was a minimum CFM, and then there was a heating CFM. You guys remember that? Okay. The max is the max. That's based on the load calculation you did. The minimum can be based on a couple of things, but it gets back to what the minimum ventilation area is. There's more than one way to do that. You can do that by square feet. If you know how many people are going to be there, you could do it by people. But you come up with some minimum based on the concept of outside air ventilation. By the way, 30 years ago, if we were sitting here, we would have called that fresh air. Finally, they changed that to outside air because, you know, there are places with air quality issues where outside air is less fresh than your inside air. So we don't use the term fresh air anymore, although when you find old people will occasionally use that expression. It's officially outside air now. And when you see the term ventilation air used, that implies that the outside air, it may be all of it and it may be a portion of it, but ventilation air relates to outside air in some manner, okay? Terminology. Now, there is a minimum ventilation, there is a maximum, which is maximum cooling load. This is now not heating, it's max heating. And this can be two numbers. It could either be 50% of that number, or it can be the calculated number if you did a heat load for the zone and you worked it backwards based on how much heat you were permitted, temperature difference you were permitted to get here. You could arrive at a calculated CFM. And so that's okay too. Mr. Arvid tells me that when he looks at other engineers' plans, because, you know, I don't know, I'm going to just swag a number and say about half our controls work is designed by others and about half is designed by us. So the ones coming from others, according to Sammy, the calculated number is typically 40 plus. 40, 42, 43. We use 50. Now, there's no significance really to either one because there's 2 stages of delivering heat to the room. You got a sensor on the wall, tells you what the temperature is. And there's a set point, right? And if we're colder than the set point, we need heat. So the first thing that it does is it sits down here at this minimum CFM and it just raises the leaving air temperature. But the leaving air temperature is not permitted to be any higher than 95. So if you get up to 95 and you're still not meeting what the room sensor is calling for, now we start to increase the CFM until we get there. Well, the only time you're going to be anywhere near this maximum CFM is if it's colder than shit in the building. When is it going to be the coldest in the building?
Morning? I'd start.
I'm hearing the right words, but
Morning?
morning. What morning?
Winter.
Winter morning. Winter morning, and there's one more thing. Monday, yes. And why Monday?
People have been in the office during the weekend.
Most office buildings, most commercial buildings, they shut off the whole system for the weekend, right? They can't do that in Minneapolis because the pipes would freeze. But here in Southern California, we don't care if it gets to be 150 degrees in the building on the weekend, and it's possible. You get some of these old, all-glass, single-pane buildings, and you have a 3-day weekend where Monday is off also, right now, and you get those 3-day weekends, it will get to, it'll be 140 plus in the building. You will find that they don't grow a lot of violets and pansies for house plants in those buildings because they can't hack that. If you've got real living plants, they're ones that can handle that heat. A modern building probably doesn't have that much glass because it would be hard to get it through the Title 24 calculation. But probably every building in Southern California that is built like a normal everyday building will have portions of it over 130 on Monday morning, and after a 3-day weekend, definitely on Tuesday morning. So bear in mind, you're starting off in the summer with a huge cooling load that morning to try to get the building down in temperature. And in the winter, you're starting off with a big heating load because the building is probably 50 degrees or so on cold mornings, especially after a 3-day weekend. You know, the Christmas holiday season type thing. Okay, so initially we're at minimum CFM and we just raised the leaving air temperature, but there is a max that we can use. And if that's not getting it done, then we start giving it more air. So on that Monday morning, in the winter, when we're trying to warm up the building, there's a very good chance that we're going to be at whatever our maximum setting is, but that's probably the only time. Now we'll talk about morning warm-up cycles later, but since we're here, the quickest way to heat up a building in the morning is with what's called a morning warm-up cycle. And that means that the main unit, whether that's an air handler or a rooftop unit or whatever it is just blowing lots of heat early. If it's a VAV system, you program everything to go wide open for air, and you're just pumping hot air into the building, and then as a room gets warm enough, gets up to set point, well, now it knows to start throttling back. Why is it energy efficient to heat the thing up as fast as you can in the morning? Just dump heat into the building until the temperature starts to get under control. Why is that efficient? Because I mean, you're going full tilt boogie, right? Your foot's in the carburetor and you're going as fast as you can go. Why is that efficient?
Takes less time to get to set point.
Can't hear.
Takes less time to get to set point.
Operating time is is the answer, right? Because you're running your whole plant, whether that's some big honking rooftop unit or whether that's your whole system. You're running it the amount of time it takes to get the system up to temperature. If on an average day it would take you 15 minutes or 30 minutes to heat the building, you know, in the spring. In the winter it might take an hour with morning warm up, maybe even a little longer. But if you don't have a morning warm up cycle built into that main unit, and you're just relying on these little reheat coils to heat your building up, shit, you might be starting at 2 or 3 in the morning. Now think about the extra hours of operating time to get the building up to temperature. And then think about, did we program that in automatically? Or are we relying on the building engineer to think of it and manually set that schedule up? And if he does think of it and he does set it up and it is comfortable, will he remember to take it back down once the warmer weather comes? The answer to all of that is usually no. So automating schedules is great, but then you have to have a criteria that makes sense to you to do it. Okay, that's all I got for this. Unless somebody's got a question, we should probably start growing and grabbing your pizza. And somebody, whoever's up there first, please pop open the salad thing. Here, Gavin brought something up. Remind me what it was. I told you I'd forget it.
The minimum CFM for electric strip.
So, Gavin was on a project where, so again, stepping back now. If it was before the middle 80s, it was common to have electric resistance heat in some way, shape, or form in a building. That was not unusual at all. Does everybody know what electric resistance heat even is? You've touched, okay, so you know how light bulbs, the old incandescent ones, got so hot? That's because if you get a filament and you run electricity through it, you either get heat or you get light or you get both. Well, you always get heat. Depending on the filament, you might get more or less light, okay? It might just glow slightly. But the principle there is that the resistance of that little filament will dictate how much electricity goes through it, which will then dictate how hot it gets. The air that you're heating that's going across that filament, it's cooling the filament, right? It's not just heating the air, it's cooling the filament. If you don't have enough air going across, the filament will melt. And so, every electric heater you were ever involved with is going to have a minimum airflow if it's heating air, or water flow if it's heating water. And if you don't meet that minimum, there's going to be some kind of a little thermocouple that shuts it off until the thermocouple gets old and breaks, and then you will have a burned out heater. That's just how that works. So, in Gavin's case, the scheduled heat for a specific box, he remembered, the schedule said 30 for the minimum CFM for ventilation. The minimum cooling was 30. But they had to set a different minimum on the heating. So now there was one more setting in here for minimum heating of 70 because there was electric strip heat in it. So always remember, if you're using electric resistance heat, there will be a minimum flow requirement to keep from damaging the heater. Okay? Thank you, Gavin. So now we're going to talk about constant volume systems. You know, we talked about variable volume systems, and you understand why it's variable volume, right? The air volume it varies. So what's a constant volume system?
It's constant.
You hope, right? Probably the most basic one is a window unit. That's a little tiny thing, right? A little tiny coil, a little tiny fan. One fan speed. They have fancier ones now that have more than one speed, but the basic thing is just one speed. How about a residential split system where you've got an air handler inside and a condensing unit outside? And we use, by the way, a lot of residential equipment in commercial applications. When I was the commercial sales manager for Carrier, we estimated that in the Carrier distributorship, which today is Sigler, we estimated that 40% of the residential equipment we sold went into commercial buildings. So it's not at all unusual to have 5-ton and under residential stuff. You know, whether it's a little light commercial package unit or whether it's a split system. It's not unusual to have residential stuff in a commercial application, just so we're really clear on that. Those are constant volume, right? Plus the rooftops you get are going to be constant volume. Historically, in our area, sheet metal were the dominant mechanical contractors 100 years ago. And they would be using evaporative cooling, swamp coolers, and sheet metal. And that was the primary thing. I mean, you know, climate's changed a little bit, but swamp coolers actually work reasonably well here. And of course, people were used to having no cooling at all, so a swamp cooler was an improvement. They had air motion, they had a little cooler air, right? Okay. So, you're used to the systems we see here. But most of the Midwest, the predominant mechanical contractors 100 years ago were plumbers. And so they used fan coil systems. And you'd have a fan coil unit, typically up in the ceiling, although you could put it under the window if you wanted. And inside the fan coil, there would be usually a heating coil, then a cooling coil, and some kind of a little filter track. And then if it was a ducted return, it'd be hooked in the back of the fan coil. If it was just pulling it out of the ceiling or out of the room, then this would be wide open. And out the front would be usually a duct, and the air would come down, and there would be one or more diffusers hooked up. So back in the day, these motors were single speed. Now today we have something called an ECM motor, and ECM motors have options on speed. Everybody doesn't use the same motor, everybody doesn't have the same number of speeds, but it's no thing to have 3 speeds or 5 speeds or however many speeds for the application. So today, many of these fan coils run on ECM motors and have a variable speed switch of some sort. Or they have a connection that they can hook to their energy management system, building automation system, and use that to control speed. I thought these were pretty well dead out here. You very seldom see a building where you got 1 million chilled water, hot water fan coils. Well, then came VRF. And VRF is just a refrigerant version of a 4-pipe fan coil system. Now this is 4 pipes. Why would I call that a 4-pipe system? Let's say for a minute, here's another one of these, and it's just got a cooling coil. It's not set up to do heating. How many pipes would be connected to that coil?
2.
This is a 2-pipe system. If there's chilled water supply and return and hot water supply and return and a changeover valve to where this could be a cooling, but it could also be heating in the winter. And you switch that over based on time of year, which 100 years ago that wasn't unusual. A lot more recent than that. I mean, 2-pipe changeover systems were really common up through about when I was born. And that would be called a 2-pipe changeover system. This, how many pipes are connected to that?
4.
4, because there's 2 coils, right? So that would be called a 4-pipe system. Forget for a minute how many refrigerant pipes you got hooked to VRF. In essence, it acts like this thing, because a VRF system, if it's a heating type of VRF system, can run in heating or it can run in cooling. There's a cheapy version of VRF. You'll see it referred to as VRF heat pump system. If it's a heat pump system, and let's just say you had 4 or 5 or 6 fan coils hooked to a condensing unit in VRF, if it's a heat pump system, it's a 2-pipe changeover. So VRF had, because all the fan coils got to be in heating or cooling at the same time, VRF has mirrored, and VRF stands for variable refrigerant flow, has mirrored these 2 systems, only without circulating water. So, where I thought before VRF became a thing, if we'd been sitting here in this room 25 years ago and I'd said VRF, you'd have looked at me blankly. You would have never heard of it before. Before that became a thing, I thought this concept was probably dead on the West Coast. But the CEC, California Energy Commission, specifically making an issue of these again. Anybody got an idea why? Why would somebody be talking about 4-pipe fan coils? We haven't talked about it yet, but are you aware that gas boilers are just about done in our state?
Wow.
All of you were young enough, well, except Alan and I. All of you were young enough. Your career will see the end of the gas boiler. They don't all have to come out on the same day. If it's in there, it's got so many years of life that it's permitted to have. But all of you guys are going to see heat pump boilers, electric power generated. And just as a side note, the justification for that is that site-generated or site-specific gas heating cannot be as efficient as the monster gas heating systems that they have at power plant. So if you're trying to address greenhouse gases, you do that by getting rid of gas usage at individual locations. And you go to electric, which ideally would come from solar and wind and tidal stuff and geothermal and all these things. In the real world, since that's not going to be able to handle everything, you want to minimize the amount that comes from power plants, and you want to use the power plant because in theory it's far more efficient. Now the fact that your electrical distribution system is only 33% efficient is an inconvenient truth for the political thing, but we are not going to fight or win that battle one way or the other in this room. What we are going to have to do is learn to deal with heat pump boilers. The maximum temperature you can get from a heat pump boiler using a conventional refrigerant is about 135. Gas boiler systems are typically designed for 180. So when the guy who works for the California Energy Commission, who I know, started modeling heat pump boilers, his assumption was that since it would be very difficult to make a 2-row coil have enough heat to do the job with 135-degree water, you would end up doing this because in a fan coil, you could get however many rows of heating coil you need. So, I guess the CEC does not change economics, but the very fact that they're using this as a baseline system for demonstrating how to comply with the new regulations suggests to me that a lot more consulting engineers are going to be using that system. So something that I thought was dead 25 years ago and then functionally has appeared with VRF looks like now because of heat pump boilers it's not going to be dead here. It's never been dead in the Midwest. You have a lot more severe heating loads, you have a lot more severe weather than we have. They also have humidity, right? So they have a lot of things that a 4-pipe fan coil does a pretty good job with. But that's where we're at today, and that's constant volume. So that kind of gets us to talking about heat pumps. We're talking about chilled water and hot water. Does everybody know what a heat pump is? Feel free to say no. Shake your head no. Somebody say no. Thank you, Bianca. Even if you know, I appreciate you saying no. The standard cooling unit, and I'm just going to draw a split system like you'd have at a house. Well, maybe I'm not. Oh, there's the other pen. So we've got a fan coil indoors, probably up in an attic with a fan. And this is a DX coil. DX stands for direct expansion. When you're talking about a refrigerant coil, the common term that we use is DX. Outside, you've got a condensing unit sitting there on the ground, right, with a condenser coil and a little compressor inside. Well, in the normal cooling scenario, this acts like a cooling coil, and because it's cooling the air, looks a little weird, right, cooling the air with a red pen, doesn't it? But because it's cooling the air, that means it's removing heat from the air, right? You're cooling the air, you're removing heat. Where's the heat go? Out here. You got a little fan on the top. You're sucking air in from the outside. Wouldn't be at all unusual if it was 95 degrees out here, which, by the way, is the commonly accepted rating point for DX cooling equipment. If this was 95, this is probably maybe 110, some number like that. And that's where the heat's going that you sucked out of the house. But there's a cool little device called a reversing valve. And so in here there will be a reversing valve and a check valve and a couple of other things, and I'm not even going to get into the details of the piping. But what it means now is that you're cooling this air. And so if it was like 47 degrees out here, you're probably pumping out 32 degree air. But you're heating this air. Right? Now it's a heating coil. And they call it a heat pump because you can pump the heat either direction. Okay? Little trivia point, which I found to be fascinating. So it's 1980, fall of 1980. I'm in Syracuse, sitting in my 8 weeks of 8 hours a day carrier training. And they pull in a guy who's about as old as I am today. So I'm 22 and he's, I don't know, 60 somewhere. And he was around. This 95 degree number was agreed to in the 30s. We've had DX cooling that long. But he was around in the very late 40s when they were trying to decide how to rate a heat pump. And instead of having a rating at one temperature, 95 outside, they came up with two temperatures. And if you look in the literature, it will give you a heating capacity for a split system or a little package unit or whatever it is. It'll give you a heating capacity at two outside air temperatures. It'll give you cooling only at 95, but it'll give you heating at two spots. The origin of that, which I thought was fascinating, but then I like trivia. The 47 was the outside air temperature where a 5-ton unit in heating, you had a 5-ton unit that would do 95 degrees, outside would do 5 tons of cooling. 47 was the temperature where it would do 5 tons of heating. It was the true reverse. 17 was provided because at that point, at 17 degrees outside coming into this unit and going through, it was coming out at about, maybe 24, because there was no more heat to suck out of the air that this technology could get. And the only heat you got was the heat of compression, basically the friction going on and the power used by that motor in that compressor. So this was the mirror capacity temperature for cooling, and this was where you were no longer getting any useful heat from the outside air. And you weren't really pumping heat. All you were doing was running the compressor to create some heat. There was nothing to pump. Now, today, this really isn't the mirror anymore. Because back in the late 40s when they were coming up with this rating system, rule of thumb was the compressor took somewhere between 25 and 30% of the power. We've got better compressors today. A compressor in a high efficiency cooling system today is probably under 20%. So realistically, the temperature at which the mirror would occur would be probably higher than this. But this number is probably still just as valid because you get to some outside air temperature where there's just no more heat you can suck out, to help with this heat pump cycle. And all that's happening is whatever you're getting out of the compressor running. And because the compressor is more efficient, it doesn't put out as much heat at 17 degrees today as something in the 50s would have. Actually, pretty significant difference. So for that reason, if you're someplace other than where we live, this heat pump, if it gets cold, if it gets particularly cold outside, isn't enough. And so what you would typically have is an electric strip heater attached right there, like Gavin had on his VAV box. You would never have to worry about a minimum CFM, right? Because this is constant volume. So that would not be an issue. But that's typically how the heat pump would operate. Stage 2, and residential thermostats were 2-stage in this area, or for this reason. You know, we're used to having a single-stage thermostat for residential and a 2-stage for commercial. But when you have a second stage of heat, you either need a 2-stage stat on the wall or you need 2 stages of logic in your programming if you're going to run it off of an automation system. So, let's see. I was going somewhere with that. Any questions about any of that while I try to remember where I was going next? When there are no questions, it means either you were really good with your explanation or so bad that nobody understood anything and doesn't want to embarrass themselves asking.
My brain couldn't process because of I was thinking that was Celsius.
No problem.
For whatever reason, I guess I couldn't process the temperature because it was so low. But I get it now. At first I was like, wait, what? Why is the temperature so low?
So I'm 22 years old. I'm in this class with 28 other people. We're engineers. And I think every one of us reaction to this was, wait, what? Just like yours.
Yeah, exactly.
Well, first of all, why would you need 2 rating points, right? The 95 points, easy to understand. Why would you need 2 for a heat pump? Now, I remember where I was going. So the electric strip heat's the common thing. But what started to become, still is, common in the cold regions is what they call a dual fuel heat pump. What would you guess the dual fuel heat pump is using for heat in addition to the heat pump cycle?
Gas.
Yeah. You put a gas, you get a gas furnace blowing into a gas heat exchanger, a furnace. Then you put a separate coil out here for the heat pump. And at some outside temperature, you switch from one to the other for your heat. Common number might be around 40. So if it's colder than about 40 degrees, you're using the furnace. And if it's warmer than that, you're using the heat pump coil. And that works really bitchin', man. That is the ultimate system. It's a little more expensive to put in the first place. It usually saves you quite a bit on your electric bill. I mean, gas, in that part of the world, you would pay less for gas in the summer and more for gas in the winter. And usually it's the flip, it's the opposite, or historically, before we got all this solar, it was the reverse for electricity. You paid more in the summer and less in the winter. So you'd look at those two things and you'd come to a decision on what temperature you wanted to switch over. But it was very popular, very popular. Find a lot of them. Any questions about that?
I was in Austin, Texas in 2021 when they had the great freeze. COVID-Geddon happened, and it was 7 degrees outside, and my dad's house has a heat pump, and I can vouch they do not work when it gets cold. No heat at all. But he's got an auxiliary coil on it, and that's the only heat we got when we had electricity. For the most part, electricity was out.
So Texas in 2021 got that abnormally cold weather, and it lasted a long time. And because the state of Texas was experimenting with how, and every state does this, how they're going to move power around, make it available, get it from other places if they didn't have enough, all that, their system completely crashed. If you Google it, I actually had occasion to Google that a couple of days ago. It said 240 people died because they had no heat for close to a week. So, you know, I don't care what you've done, you can still have things happen that are beyond your control. A lot of people ended up buying little generators. Okay. So VRF thing. So I'm on several ASHRAE committees with a bunch of Canadians. And every one of them just would look at you across the table and tell you that VRF heating ratings were utter bullshit. That they never came out close to doing what they said that they would do. Now, the Canadians understand the concept of a heat pump snowstorm. We in our northern states do the same thing. You wouldn't have an outdoor heat pump outside your house sitting on the ground because the snow builds up, right? So you would have a stand that it went on that would be, you know, some height off the ground. I remember growing up, my neighbor had one, and it was about that high. And if the snow got up higher than that, you got out there with your shovel and you moved it because otherwise your heat pump would freeze up. Oh, that brings up an interesting point. So let's say that it's cold outside. And remember, we're heating indoors, so that means we're cooling outdoors. And if we're cooling, do we get condensation on the coil? And it's below 32 degrees.
You freeze.
You freeze. So they have what's called a defrost cycle. And the little brain inside the heat pump is aware of this, and it monitors what's going on for the coil temperature, and it will have a defrost cycle that might run 3 minutes or 5 minutes or 10 minutes, depending on how cold it is. During that period of time, what temperature or air is being blown inside? Cold, because it flips over to have heat on the outside, right, to melt the stuff off the coil. So all of our heat pump boilers, and I remember the first conversation I had with a equipment rep, who was selling heat pump boilers. And I said, what do you do about defrost? And he looked at me blankly. Well, of course there's defrost built into these things. But think about it. What's your average water temperature if you're spending 10 minutes every hour doing the reverse thing? It's working like a chiller for 10 minutes out of the hour. What does that do to your average water temperature in your heating loop? And if you've got a bunch of them, and we frequently will have a bunch of them because a little Raypak gas boiler the size of this thing, or maybe just a little bit longer, you could get up to 2 million BTUs out of one of those, and you'd need, at 400,000 a pop, which is about the biggest that they come, you'd need, what, 5 of them to have equivalent capacity to that one boiler. So at least you got 5, right? And you could set them up to defrost sequentially, in theory. And so maybe you wouldn't just totally dive your hot water loop temperature, but you're going to have an impact. Now, could you add little mixing loops and do all kinds of other stuff? Yeah. At more cost, at more complexity, but could you? Yeah, you could. I don't see most people doing it. So anyway, that's your little heat pump conversation. And that brings us to fans. So if we had a fan wheel, there's 2 ways we can construct that thing. For lower static pressure, don't have to push air against as much of a duct system, we would normally use forward curve fans. And a typical forward curve fan would have 50 or 60 of these little blades. People call them squirrel cage fans because if you've ever seen the one that your hamster or your squirrel or your mouse runs on, it looks like one of those. And these are just little cups. We're spinning this way. The cup's going the same way that we're spinning. So it's essentially throwing the air. These are virtually always in a scroll, which is a surrounding thing that looks like this. the air comes out, the air goes in the side. Now these fans are available in two flavors, single inlet and double inlet. How many entries to a double inlet fan are there? Somebody say two, please. If I was looking at this plan view, here's my fan wheel, and there's my shaft, and I'm spinning like this, and my scroll extends out here, and I'm blowing air. Air can come in this side, or air can come in this side on a dual inlet. But you can also get fans with a single inlet. The fans with the single inlet have a housing, like this scroll, and it only comes in one side, the air. Let's talk for a minute about why would you ever use a single inlet fan? Any ideas?
Maybe like clearance if you're next to an exhaust or something.
That's the first thing that comes to your mind. But let me show you the fallacy of that. Gavin, that's a totally logical answer, and a lot of people would say that. But if this is your wall, and you don't have much space, and you put a single inlet fan here, again, I'm looking plan view now, so here it is. I got a shaft, and I'm only taking air in this side, and I'm blowing it out, right? I still got to change that bearing someday. So I have to have access to both sides. I actually checked with Brian before this class. I said, Brian, I can only think of one real reason to use a single inlet fan. I told him what it was. I said, can you think of anything more? And he said, no. Why would you use a single inlet fan?
This is a ducted situation, non-ducted.
I haven't said nothing yet. It's if you're going to duct the inlet. Let's say that you're taking air out of a room and you got the fan up on the roof. If you're going to duct into it, a single inlet fan is the practical way to handle that. Okay? And so a ducted return right to the fan, and there's not a lot of these applications in cooling and heating, but exhaust fans, yeah. You'll see big exhaust fans that are single inlet on a roof with a duct serving them and hooking up. So now that I've discussed the only way I can think of why, if any of you think of some other application, let me know. Brian and I were kind of stumped. We couldn't think of anything else. So the rest of the ones that we use are going to be dual inlet. Okay? And I already started telling you about forward curve fans. They are the most common. But this is just a little fan scroll. I mean, what's holding that fan scroll in place? Typically, we end up using these in what's called a cabinet fan. And a cabinet fan is this box that the fan's inside of. And you probably have a flex connector right here. And there's a frame of some kind that goes up and holds the bearing on each side so that, you know, the shaft that fan's on is suspended. And maybe if it's internally isolated, maybe we got some springs under here. And the motor is sitting here with its pulley, and they're got a belt. Most of these are not ECM yet. One of the reasons is that ECM has got kind of a practical horsepower limit of like 15 or 20. You can get them bigger than that, but you don't see it very often because their price goes nuts. So when you get bigger than that, you've got a conventional thing like this, and if you wanted variable speed, instead of ECM, you're doing what we've always done, which is a variable speed drive with one of these, okay? So this is a cabinet fan, what I've drawn here, and this is the basis of an air handling unit. The standard conventional air handling unit is a cabinet fan that you then hook a bunch of other stuff to. For instance, you could have a coil section with a drain pan and a drain and a cooling coil. You might have a preheat coil in here too. Now that's a preheat coil. If the heating coil was here, what do you suppose they'd call it? Somebody say reheat.
Read.
Okay, so here we got a cooling coil. If we had a heating coil here, it's reheat. If we had a heating coil here, it's preheat. Why would you pick one over the other?
Well, if you're worried about condensation with the cooling coil, or I'm trying to think.
If you're doing dehumidification.
The guy who's actually programmed one is sitting back here. He said, if you're doing dehumidification, yeah. And we'll talk about psychometrics later on down the road, but if you're trying to get rid of moisture in the air, one way, the conventional way, is to cool the shit out of it here, because that's what gets the moisture to come out, right? And then reheat it back up to whatever temperature you needed to have in the room. That's not the most energy efficient way to handle dehumidification, but it is the old tried and true conventional way, and it works.
Kind of like defrosting your food and then cooking it.
Kind of.
Okay. In terms.
Uh-huh. If your food was air, yes. Uh-huh. Now, just from a cost standpoint, do you think that, just looking at this, does it strike you that preheat or reheat would be a cheaper air handling unit?
Preheat.
I got one vote for preheat.
You're asking which one's cheaper?
Which one's cheaper? Would the piping be any different? No. Would the ductwork be any different? No. It's just that device, okay? Preheat is right. A preheat section is this little piece of wussy tin that's got a heating coil in it that you bolt on the back end. A reheat coil means we have extended the cooling coil section with the drain pan and all that other shit to make room for this thing. On top of that, maintenance-wise, the typical factory reheat coil gives you about this much space between the two coils. How the hell do you clean from both sides of those coils? I'm not going to say you can't, because if they built a little bitty door in there, and you can stick a wand in there with like a very light duty power washer, and you don't want to hit these with a heavy duty power washer, you'll bend the fins and destroy the coil. But could you wash it with a wand and could you? Yes. Does anybody ever wash a coil if they have to go to that extent? No. So, what this gives you is the option of having just an access section with a door on it. And these are like 9 inches is a very typical airway length, so it's not like they're huge. Now you've got a preheat coil. And now you've got a whole door, you can get in, you can do all kinds of neat things, which especially for the cooling coil, which is getting condensation on it, it has shit growing on it. It's really good to be able to get to both sides. The one time you really probably don't have to is if you use UV lights. If there's no heating coil here, and I have a couple of UV lights there, those just work miracles. Carbon-based life forms don't like UV light. And if you put the bulbs in, they do well, they're too expensive to call them a bulb. They call them an emitter. It's like how Liebert doesn't have thermostats on the wall. They have a controller. Okay. But it's a bulb. The thing to understand about UV bulbs, and they work great. I mean, they'll even clean up an old grody coil. I have stories. But the thing to understand about these is they start out at a particular emitting strength. And that dies linearly over time. And when they get below a certain level, they're not killing carbon-based life forms anymore. Which means you have to have your little meter or you just change them every year and a half. None of them will go 2 years in a normal office environment before they're down below the level that they don't do anything anymore. Now, if you were stupid enough to look at them, and by the way, if you put these in, these bulb kits come with little stickers you put on every door that can get near it that says, "Don't go in here while it's on," and you've got to have a light switch thingy. It's really hard on your eyes, okay? It will also degrade stuff in here if it's shining on it. It's hard on fan belts. So the emitter typically will have a reflector, something like this, so that the light's only going the way that you want it to go. It doesn't bother the fiberglass insulation, or if it's a double wall air handler where you got a sheet metal layer on the inside and on the outside and then the insulation in between, doesn't bother any of that. And if you're running your wiring here in conduit, you're okay as long as it's metal conduit. It could be metal flex, it could be hard metal, it'd be fine. You can't run electrical wiring to the motor if the UV's shining on it. You can't run electrical wiring in where it's exposed or in seal tight, the plastic flex. You can't, because it'll eat it up. UV does that, right? So that's why you want your emitters set up so that they go the right direction. I won't go into a whole lot more. If you're curious, ask me. Like I said, I have stories. But UV works. And we've had to retrofit UV in where somebody put something in, there was just no physical way to do any cleaning. Changing them out is expensive. They don't give those emitters away. Guys got to wear cotton gloves because you don't want the oil off of your fingers on those bulbs, because what ends up happening is the dust sticks to the oil and then the UV screws up its own glass bulb. So you have to put them in very carefully. One example. So the City of Ontario's police department sits right adjacent to their sewage treatment plant. And it's to the east, so whenever you've got the normal, other than a Santa Ana, the prevailing wind is blowing from the sewage treatment plant to the police department across the little access road. So not only do we use carbon filters, for obvious reasons, in those 50-ton rooftop units, there's 6 of them and a 30. Not only do we use carbon filters in there, but we had to put these in because what you really don't want is dust that's coming from a poop plant all over your wet cooling coil. This is not good, not good. So that's what we do. But because these carrier units were not built with the idea these would be in there, there's physically not room to get them in there. We have to take the top off to change the bulbs. So not only are the bulbs expensive, you can imagine the labor involved to take the roof off of a 50-ton rooftop unit in order to change, or at least that section of the roof, to change the... So it's not simple. It has to be thought out. But it is a viable technical solution. Okay, so we talked about preheat, reheat. Where we started this whole conversation was with a forward curve fan, which is abbreviated FC. And like I said, the typical fan wheel will have 50-ish blades. But that's not the only kind of fan wheel. The reason that this is more efficient at lower statics is, remember I said there's a cup, and we're spinning, and we're throwing the air. But the more static you're having to push against, static pressure, the more duct resistance, the more filters you got, the more coils, the more resistance to move in the air. The more you've got, the more you need a fan that's designed to generate pressure as opposed to throw air. And so that is what is typically called a backward inclined, or the more efficient version is an airfoil wheel. So if this is the inside where the air goes in, and that is the outside edge, instead of having a bunch of forward curve blades, what we have instead, first of all, the term backward inclined should give you a clue. If we're spinning this way, It's doing this. And so and maybe a dozen blades would be a common number. It's not trying to throw air forward. In fact, the blade's tipped the wrong way to help throw air forward. All this is doing is generating pressure. Now, if you put one of those in a fan scroll, then you can direct the pressure, right? You can give it instructions on where it's supposed to go. And so here you are. You've got your fan scroll. You've got your BI fan. It's generating pressure in here, and it's basically just being forced out. The highest airfoil fan pressure I was ever involved with, and this wasn't for air conditioning, was 30 inches. That's a lot, guys. The typical forward curve air handling unit with a 2-inch pre-filter and a cooling coil and maybe a heating coil for morning warm-up, going down and feeding a duct system with some VAV boxes. That's a more than 3, but probably less than 4.5-inch situation. If you're in a hospital, though, the current hospital requirement, if you're in a operating room and somebody's going to be cut open, is 3 levels of filtration. You've got a 2-inch pre-filter, which is just trying to protect the coil from getting a bunch of dirt and junk on it. Then you got an intermediate filter, which is probably MERV 14 or 15, and then you've got a HEPA. We talked last time about the surgery center over in Santa Monica, where we put the HEPAs in 2016, and the pressure differential across them is getting close, but still is not requiring a replacement because we replaced the intermediate one every year. But if you're permitted to get your HEPA up to 2 inches, and your intermediate filter is running at least 1 inch, and you got a cooling coil that's probably over 1 inch, forget the duct system, right? Pretty quickly, you're out of the range where you want to be using a forward curve. And so hospitals almost always are using not a BI, but the more energy efficient airfoil. BI fans with that straight blade, they can be made hell for stout. You could have a 10 gauge blade there. What's 10 gauge thickness wise? 1/8? Quarter? That's thick, heavy. They use those kinds of fans for material moving, like sawdust, or where there's stuff in the air, not just air. And so that's where you'll see BIs used. I can't think of. What do you call the pharmacy ones, the dust collectors, where they're taking all the pill dust that's scattered around and exhausting it, and they got to clean all that up before they dump it out into the atmosphere.
Bag filter?
Thank you. A bag house, yeah. So BI filters are not unusual for bag houses as well, although it could be an airfoil. So what's the difference between a BI and an airfoil? Well, everybody knows what an airplane wing looks like, right? That teardrop? That's an airfoil. You got a bunch of those. And there's a significant efficiency difference in terms of how much air you move relative to how much energy you waste if you use an airfoil instead of a BI. And so you're in our industry, you use a forward curve if you can. And if you get to the point where you really can't, and you don't want to push a fan just to the max RPM, because every fan will have a max RPM. Why is there a max RPM for a fan? Oh, come on. Why?
So you don't overspin.
Overspin? Yeah. What happens if you overspin?
Friction.
Pieces, right? You don't want pieces. They'll come apart. Okay? Now, if its max RPM is 900 and you get to 901 for a moment, will there be a problem? No. First of all, there's a safety factor built in. But if your max RPM is 900 and you're spending all your time at 1,000, will you get metal fatigue and are you likely to have a failure? Yeah. That's why there's a max RPM, okay? So you don't want to select a forward curve wheel against 5 or so inches of static. Now you can get forward curve wheels that can do that, but they're not usually what our air handler manufacturers. That's not usually what Carrier and Train and York are sticking in their cabinets. They're not thinking you're going to go 5.5 inches with a forward curve wheel, and they're not built for that. So you have to be very conscious of what's the max RPM. Not saying that that fan wouldn't move the air you want under the conditions you want. I've known people who said, well, it's VAV. How often is it at full output? Like very little, 1% or 2% a year. So if I selected a little past the max RPM, is that really a risk? I don't know. That requires judgment, right? It's not a good idea, though. Okay, so that's airfoil. That's BI. You know what a forward curve is. This is a scroll. You know what a cabinet fan is. You know single inlet versus dual inlet. The only thing that leaves, and we're going to finish with it, is what's called a fan wall. But before we get to fan walls, we have to talk about what in the 80s we called a plug fan, but then we all had to learn the real name and start calling them plenum fans. So that's a single inlet fan that's crossways. How many of you remember what engines in cars looked like in the 60s? Had a straight engine and the transmission was right behind it, and then there was this thing that went back through for your car because you had the transmission hump in the middle, and then there was a drive shaft, and then the wheels were in the back, right? And then when we went to the little overhead cam, really fast engines, they turned all the engines sideways. Why'd they do that? Well, yeah, that's true. That went with that. But why did they turn the engine sideways? It was space, right? Now the transmission had to do the more complicated job. Where we would have a fan, like I drew it, a plenum fan, as a plenum, might have duct connections coming out of it, might have a cooling coil in here and then duct connections coming out of it. Because, oh, we hadn't talked about draw through and blow through. Oh well, I knew I forgot something. But a plenum fan is sideways. It blows like that. It takes air in this way, single inlet, and blows it out this way. Pretty cool, really. You have a motor sitting here. It might be direct drive and you're just variable speed. The older ones had belt drives, the motor would be off to the side and there'd be pulleys and stuff. This is pretty much what you see. This design is less energy efficient. If you go with a bigger wheel, you might be able to partially offset that, but you save real estate. You can use a plenum fan blowing into a plenum. That's why they call it a plenum fan. And you probably cut at least a third, maybe half of the airway length out of the whole equation. So if you're short on floor space, it's a good solution. And then in the last, I don't know, when did we start seeing fan walls?
15 years.
15 years. So here you got a plenum that you're blowing into, and it might have a duct coming out and a duct coming out and whatever you're doing. And maybe this has got 4 fans mounted with the motor and the fan. And if you wanted to, you could put all 4 of those on one variable speed drive. so that they ramped up and down together for your variable speed. You wouldn't have to. You could split them up some way if you wanted. You also have the ability to turn off one of those. But let's say that we had 3 of them running and we turned that one off and we didn't do anything else. What would happen? What would happen at this opening where this fan's sitting?
Take like a backdraft.
If we're putting air in here, in here, in here, and we shut that fan off, the path of least resistance is for the air to come right back out through there. So if I turn this wall, and yes, Aaron, you were thinking about the right thing. If I turn this wall sideways, and I've got 4 of these, and then there's 2 behind it, each one of them needs a backdraft damper with a pretty good seal. And it's got to be pretty heavy-duty backdraft damper. There's all kinds of backdraft dampers out there, ranging from the weakest sisters you've ever seen to some really heavy-duty things. You need a pretty good one here. They come in 2 flavors. They could either have a spring that holds them shut, and then when the fan blows, part of the static pressure it has to overcome is to blow that thing open, right? That's the less expensive and generally lower pressure version. If you got a fan wall, this probably has an actuator and is powered open and closed. So the sequence that you need for opening and closing this damper has to be part of the control sequence. And it's probably best if you shut that before you take this thing offline. Because if you don't, you will get that other stuff happening that you just don't want to have happen. So each one of these has got one of those, and they double for service. Let's say the motor burns out on one of these. You shut the backdraft damper. You don't have to worry about sequencing it because the motor burned out. It's dead. It's not running. You've got some kind of a fan status monitor, right? You've got, we used to call them a donut, but a toroid on the power coming to the motor, each one of them. And if you don't see current, it's dead. That would tell you to shut the damper. You might have a pressure switch. You might have some other things as well that you use to shut that backdraft damper. Assuming that it worked and the actuator wasn't burned out or something like that, then you could then replace the motor, you could take the fan out, you could do whatever you had to do. You could replace bearings, whatever you might need to do, you can do with that backdraft damper shut and the other 3 running, in theory. Is it a good idea to be working on one of these while the other 3 are running? No. It's a very bad idea. But if you were at a nuclear plant and that happened, you'd get your ass in there and you'd work on it whether it was running or not, right? You could do it. The problem in trying to replace a motor in one of these while the other 3 are running is you're in a gale force wind here. Something falls out of your pocket. Where's it going to go, right? So it's not a safe thing to work on this. So what you would normally do is the other 3 would run and you would wait until night or weekend or whenever in the schedule you could get in there and do your repair work. Okay, so that's a fan wall. And they call it a fan wall because you got a wall and a bunch of fans. Hey Matt, what's the most fans you've ever seen in a fan wall? 12? I don't know.
That's the number that came to mind. There's more. I mean, that's the most I've seen.
Oh yeah, there's no effective limit. It's just structural. Making this panel, think about what this panel's got to be. That's a pretty stout panel. It's probably involved in the weight support, although you've got probably supports built into the panel. But you can go as high or as wide as you want, you know. I mean, you could have 3 high, 3 wide. You could have 3 wide and 2 high, whatever you want to do. There's even fan walls with only 2, but I don't see many of those. Usually you're dealing with at least 4 if you're talking about a fan wall at all. 1, 2, 3, Macarena. 4. All right.
Yeah, it's also.
Well, that gets us through what we were going to talk about today. So I guess the timing is good. Does anybody have any questions about anything that we talked about?
Yeah, I have a question about the backdraft dampers sequencing. So you mentioned sequencing it closed before you turn the fan off to avoid spinning the fan in the wrong direction.
Well, it depends on how many you're going to modulate off or not. That comes out of the sequence.
Yeah, say you're just modulating one closed. Would you have to worry about generating a high static pressure behind the backdraft damper?
You shouldn't have to worry about it because you should, well, so, and this is actually a pretty good point. Okay, come on. Which one of you guys is doing this? No. Yeah. So Aaron brought up a good point. And this is something to think through. He said, okay, well, if I've got variable speed here and I've got backdraft dampers, control sequence-wise, what happens first, what happens second? Well, my first question is, are all of these on one common VFD?
Let's say no.
Okay. Let's say we spent the extra money and we've got a VFD for every one of these so that it's 1-to-1 between the VFD and the backdraft damper. Well, then I'd probably be slowing them down at the same time I'm closing the backdraft damper. But let's say that we went the cheap way, which is not unusual. And let's say we had one VFD handling all 4. Usually they'd have 2, right? So that you've got some level of redundancy. You got one handling 2 and one handling 2. That would be more common, okay? But if it was 1-to-1, then you would have the speed of the fan going down at the same time you're closing it. But if you had 4-to-1, you're not going to shut all 4 of those fans down to shut one backdraft damper. Which means now that you're going to have to pick a heavy... You cannot screw up by having a heavier duty backdraft damper. You just can't. If there's a choice between the heavier backdraft damper and the lighter backdraft damper, that is a place to put money on the heavy backdraft damper. Because they are a weak link. And if you're picking the actuator, you have to pick an actuator that's going to be strong enough, have enough torque to be able to close it while it's running. Now, if any of this happens and it doesn't work that way, then the fix afterwards is you slow the whole assembly down to some speed, 70%, 50%, I don't know, some number. You probably try it and see what works. Okay, that seems to work okay. Yeah, the actuator's not laboring too much trying to close that thing. And then you bring it back up after it's closed. And the logic there is, well, nobody's going to notice that we cut the airflow down for a minute or however long it takes the actuator to shut the backdraft damper, right? But that's one of those details that actually needs some thought and some judgment. So when you get into a scenario with a fan wall where you're trying to decide how you want to program the two together, the speed and and if your design is that you're going to take individual, you may not choose to take any offline until you get down to such a low speed that the fan's not working anymore for you. There's probably some minimum speed for one of those fans. I don't know, 20, 25%. There'll be some number you don't go below. But if you're that low, closing a backdraft damper is easy because you're not putting much out. So anyway, that is something that actually requires some thought. We do a pretty good job, not a great job, but a pretty good job of our controls guys when they run into something like this, talking to whoever the design engineer was that put it together to make sure that they have the same understanding of the design intent. We do a pretty good job of that. The people who do a shitty job of that are the independent controls contractors. Because the job's already designed, it hits the street, and for the most part, the design engineer would rather not take the responsibility for the controls design. and he'll give, some general statements about what he expects to see, and then he'll tell the control contractor to do that. Okay, but does the control contractor come back and actually ask the design engineer when he has questions? No, and the reason that they don't is because they're always behind. The last guy on the job is always the controls contractor. The controls contractor is at the mercy of every other trade that's had a delay. So by the time it gets to where you're trying to get the controls working, there's a gun to your head. Everybody's jumping up and down. They want to get their temporary occupancy permit, right? And so I'm not picking on the controls contractor. I'm just saying the way the system is set up, it is stacked against that poor controls guy. If he didn't get all of his programming done way ahead of time, to where he can then put through an RFI and he can find out the answer, all of which takes time, right? If he's running behind and he gets to that point and he's just ahead of the field guys with his programming, and I'm going to tell you that if you go to Climber Rec or Lower Level or any of the independent guys out there, that's exactly how they're operating, okay? They are one step ahead of the field. They don't have time to get answers from the engineer. So they do what makes the most sense to them, and you know what? Usually it works. And if it doesn't, then somebody has to fix it afterwards. One of the advantages of having the two people in the same building is, I would say, shame on you to anybody in the controls group who has a question about something that takes some judgment. I know everybody's default is, we'll go ask Alan. Well, okay. I will say Alan is absolutely the best diagnostician in the company. You can get an answer out of Alan that might even be right about 20 words into the explanation of what the problem is. He's very good. But the right way to handle this when you have a judgment question is to drag the individual who did the design, who can't be more than 100 feet away, into the conversation. If you're going to go talk to Alan, that's great. What would we do? And Montalvo has almost become a junior Alan that way. He's very good. Michael's come a long ways. But get the engineer that designed it involved in the conversation too, and then you won't end up with accidents, right? We have that opportunity, and shame on us if we don't take advantage of that. Okay, that's the end of that sermon. Any other questions? Okay, guys, go earn money. It's Friday afternoon, man. I bet you get minimum distractions this afternoon. What time is it? I bet most of the field guys are cheated by a half hour and they're already on their way home. So you should have minimal distractions. You should be able to get a lot done.